let's finish our discussion about this paper by completing the last piece. We're going to show you how may we find the optimal plan. The optimal plan by mixing the fixed fee plan and the usage-based plan. Okay, so we need some assumptions for we to complete this part. First, let's assume that our cost, transaction cost C, satisfies certain conditions. If Q is 0, then it's 0. Also, if Q is positive, we have a fixed cost and then a variable cost. Okay, the fixed cost is non-negative, so that means if K is 0, there is no such fixed cost. And also C of Q is non-decreasing in Q. Okay, so naturally we can say that C of 0 is 0, because otherwise we can take those parts into capital K. So this is our first assumption. Also, we need a technical assumption regarding regarding the curvature of the small c function. Anyway, that's technical. Finally, we need our old friends. We need the increasing failure rate condition for the type distribution. Okay. With these mild technical assumptions in mind, we can show the following proposition. In this proposition, we're going to write down, or we're going to find the optimal Q-tau pair, the optimal usage-based pricing plan, when we are not allowed to offer a fixed fee pricing plan. Okay, in this case, the optimal plan, optimal menu satisfies the following thing. First, there is a threshold theta k such that below theta k, we're not going to serve them. We will just offer 0 to them. Above it, the optimal quantity and the optimal transfer are defined in this way. Okay, things are so ugly, right? But you see some familiar faces. First, okay, the inverse failure rate. Second, a weird integration with theta as the upper bound. Okay, this somehow reminds you about. It seems like this solution is somewhat similar to our solution when we were doing monopoly pricing problem, right? So that's something we're going to show you later. But now I need more spaces to complete proposition 3. So I need to find a way, I need to have a way to define theta k. Okay, we can say that theta k is the minimum theta that satisfying these inequalities. Okay? Again, this is something that looks ugly, but something that has some familiar parts. So now let me try to explain to you what does this solution tells us, okay, by comparing this to the solution of our monopoly pricing problem. Okay, so let me try to do this. The first thing I want to show you, I want to remind you is about the setting of the monopoly pricing problem. In that case, the U function is what? It's theta times V of Q, okay? And Q is a function, blah, 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 you know it. And also, C of Q is just CQ, okay? Our setting in our previous week, okay? Let's see what's going to happen if U is in this form and C is in this form. Okay, in that case, these two lines, well, let's translate these two lines. For the first line, u with first order derivative with respect to q, we get theta v prime of q. And then the second term, u first q and then theta. First q and then theta. That's all. And then multiply by the inverse failure rate. Finally, this guy equals C prime. C prime is nothing but C only. Okay? So if you do this, oh sorry, these are theta Q star, Q star. Okay? If you do this, what does that mean? That means your optimal Q is determined in this formula. Is that true? This is exactly how do we find our second best consumption level or quantity in our monopoly pricing problem. Okay? I hope you feel familiar about this because you're going to take your midterm exam. Okay, so quantity is defined in the same way. How about the transfer? Okay, so let's see what's going to happen with our transfer. This u function, okay, u function is this guy. And how about that? That's going to be an integration, and let me remove this part. That's going to be an integration from theta k to theta with a first order derivative with respect to theta, v of q star of x dx. Okay? If you go back to check your notes, this is exactly how you define your optimal transfer. Okay, this is the welfare or utility, and this equals to tau plus this part. Okay, well, something you had in your previous lecture. So that tells us, oh, so this solution is nothing but a generalization from our particular format. Previously, we assumed u is in this format, but actually the problem can be solved even if we are facing a more general u function. Okay, that's the idea. Finally, let's discuss what this quantity means. So remind yourself that when we were dealing with the monopoly pricing problem, eventually we are solving or optimizing the following unconstrained problem. Okay, so go back to and check your notes to see this is indeed the last thing we want to optimize when we were with our monopoly pricing problem. What do you see here is that when you have this function, you need to somehow do a pointwise optimization to take the first order derivative with respect to q of theta for this formula. And does that fit our more general function here? That's true. This first part, u, is nothing but this one. Okay? And then minus this thing, okay? V is nothing but u first order derivative with theta times the inverse failure rate. And then this part is the cost. Okay? Is the cost. So theta k is nothing but the cutoff or the type that makes this thing non-negative. Okay? Theta k makes these things non-negative. For those types that this part is negative, we're going to abandon it, we're going to exclude them from our service. Theta k makes this part non-negative. Okay, so now you can fully understand proposition 3. Okay, it's nothing but a generalization from our monopoly pricing problem. Yeah, so if you go through the proofs, yeah, you will be able to understand it. Okay, so now we know if there is no such fixed fee option, how may we find the optimal pricing plan? But that's not enough. We want to ask, how may we optimally mix these two plans? And then naturally there is a question. If I first find the optimal pricing plan, and then I add the new all-you-can-eat plan inside, probably I need to readjust the original plan, right? So if that's the case, then jointly, if I want to maximize everything, it would be hard. Yeah, so that's the issue. And eventually we will tell you that there are some ways to deal with that. But before that, okay, let's say something more about this problem. And okay, it's here. Okay, for the usage-based only problem, okay, we still have some implications to tell you. Okay, this has been mentioned by me. So if you are not allowed to offer the all-you-can-eat plan, finding the optimal schedule is kind of easy. Okay, we say it easy is because it follows the standard way of solving a problem. Yeah, so that's some kind of easy thing. Okay. Second, the second observation is here. Suppose k is non-negative. That means suppose there is a transaction cost for all the possible quantities. Okay. In that case, we need Q star of theta k to be strictly greater than 0. Why do we have that? Suppose k is positive, then this part, the right hand side of this is positive. If Q star of theta k is 0, then the first part will be 0, the second part will be 0, nothing will be left. You are not able to make an inequality here. Okay? So if k is positive, okay, if there is a transaction cost, then we will really need to make Q star of Q theta k positive. Okay, we need to fit this particular type a positive amount. Okay, graphically that means the following. Suppose I want to draw the relationship between theta and Q star of theta, the optimal consumption. It depends on where theta k is. Below that, the quantity is 0, right? But above it, the function is discontinuous. It will be something like this, and then this part is exactly our Q star of theta k, which is positive. Okay, so you can see there will be a gap between theta and in this curve. Now let's discuss why do we have this, or sorry, what will happen if we have this. Suppose you are asking what will be the true price schedule as a function of quantity. Okay, you are asking 1 and P3, what's the price? 2 and P3, what's the price? Okay, if you really want to transfer the optimal Q tau pair into this price schedule, you are going to see something like this. You want to ask what's the relationship between Q and the price? Then here you're going to have, for Q star of theta K, you have a transfer tau star of theta K, right? If I want to eat this amount, I need to pay this amount, and no, this is the situation. And what's more interesting is that below this quantity, because I do not want to serve anyone, so the price here will essentially be the same. What does that mean? 1 MP3, $10. 2 MP3, $10, blah blah blah. 5 MP3, $10, and then above it, I have a variable pricing plan. Okay, there will be a minimum price. Okay, there will be a minimum price for you to enjoy the service. Even if you only want 1 MP3, you need to pay the minimum price. The same as enjoying for 5 MP3 songs. Okay, as an example. Okay, so if you think about the practice, this seems to be true, right? In many situations, there is no such way for you to say, I want a very tiny consumption with a very tiny pricing plan. For example, MP3 songs, or if you want to buy 3G data plans, you are not allowed to say 1 megabytes how much money, 2 megabytes how much money. Okay, there is a minimum price for you to enjoy the minimum level of consumptions. Why do we have this? Because this is a continuity. Because there is a positive transaction cost. Okay, we can show you that if there is no such positive transaction cost, this is not going to happen. I mean, this may not happen. Okay, so the existence of transaction cost somehow help us to explain why do we see this minimum price practice in the current industry. Okay, yeah, that's something we have in mind. Okay, now is our last step. I want to show you how may we find the optimal joint pricing plan. Okay, and essentially that depends on proposition 4, and that's going to allow us to find the optimal pricing plan. Okay, and proposition 4, the conclusion is surprisingly clear. T star, the optimal price for the all-you-can-eat plan, and the Q star and tau star, these two things are independent. What does that mean? That means when we want to optimize everything, we can follow the following steps. First is to solve the problem without all-you-can-eat plan in proposition 3 to find this optimal plan. And then we're going to find a cutoff, the optimal cutoff, okay, so that above it, people will switch to the all-you-can-eat plan. Okay, we know there will be such a cutoff, and we have a formula for that. Okay, and finally, we're going to use this to define our optimal price. Okay, here we have a lot of notations, but it somehow just means the the transfer payment should be the one that make the optimal type, the optimal cutoff indifferent between the all-you-can-eat plan and the original usage-based plan. Okay. So now I'm not going to prove this, and I'm just going to try to convince you that this is true. Okay. I would say this result is too strong. Too strong, that means I personally cannot explain why this is true in practice. Okay? Mathematically, why this is true? If you think about solving the problem with a T star and the Q star and the theta star, okay, you know when we are solving any optimal contract design problems like this, we look at the critical component, the critical quantity, which is the quantity, or the quantity in this case, okay, the external variable is the quantity here, okay. Typically, when we solve it, we do a lot of things. Eventually, we need to do a first-order derivative with respect to the quantity, right? When we do so, this function will be modified. Okay, we get the first-order condition. The tau function will get the first-order condition, but this T star, this is a number. This has nothing to do with Q star, right? So when we do a first-order derivative with respect to Q, T star will disappear, okay? And that's why eventually you can see the optimal plan, okay? In the optimal plan, these two parts are independent. Okay, so that somehow explains to you why we have this. Or intuitively, what does that mean? Originally, you have all these consumers. Okay, you know in your optimal Q-tau pair, some people will participate, some people will be excluded by you. And here, when you introduce the all-you-can-eat plan, you know some people will switch to your all-you-can-eat. How about those remaining guys? Essentially, you are asking, do you need to redesign the plan? And the answer is no. Because this person are still there. They are not really changed, right? Some people leave, but you are still there. How to optimally price you? The same. Okay. So that's the intuition about why, after you introduce the new option, for those old consumers, you will still use the same pricing plan. Okay? That's the intuition. At least mathematically, within the framework of this paper, you know that's true. There are many possible ways to modify the setting so that this is not true anymore. Yeah, but at least for this particular setting, this is the case. Okay. So finally, let's make a remark about introducing this thing. What will be the implication to social welfare? Suppose you have the optimal plan. Okay. Under this, consumers earn something, the firms earn